Okay, good afternoon. Today we're going to look at two very important components in electronic circuits, Zener diodes and op amps. So Zener diodes is something that we will learn in detail in 315, so in spring. But op amps is a device that is typically learned in the first year of EE classes. And we are not looking at the op amp or the internal circuitry of an op amp, but we are looking at an op amp as a building block. We use it as an off-the-shelf component, and then we create circuits using those op amps. So we are not focused on the internal structure and the internal workings of the op amp, but how to use it as a building block and create other circuits. And so that's what we are focused on. All right, so it's okay. All right, op amps and Zener diodes. First up is Zener diodes. Okay. The special thing about Zener diodes is that they are fabricated specifically to operate in the reverse breakdown region. Okay. So normal silicon diodes, we know that they are one-way devices. We have the anode and the cathode. When the anode is higher than the cathode, diode is said to work in forward mode of operation or forward bias. Current flows in that direction. If you flip the terminals, if you apply an opposite voltage, meaning the cathode is higher than the anode, then it's said to be the reverse mode of operation. Diode is, for all intents and purposes, completely off, and there is no current flowing through in the opposite direction. That holds true until the junction between the two terminals breaks down. Okay, when the junction breaks down, there's a huge influx of carriers crossing through the junction in the opposite direction, and hence there's a large reverse current that starts flowing through it. And that is represented by this graph right here. Okay. Here we have, let me draw out the X and Y axes. This is the diode voltage, positive diode voltage. This is negative. The negative in this, the negative simply refers to the fact that it's operating in the reverse bias, or the reverse mode of operation, meaning the cathode has a higher potential than the anode. Okay. And this right here, let's see, 0 is here. This is the diode current. And I would say this is negative. And again, for both negative voltage and negative current, all it means is that it's flowing in the opposite direction, right? Diode positive reference is always at the anode, negative is at the cathode. If you flip those references, then we say it's negative voltage and negative current. What I want students to understand is to not get too bogged down in the internal workings of these devices. Okay. So diode current flows from anode to cathode. Zener diode is the exact opposite. So here shows you the forward characteristics, forward bias, after it crosses the diode turn on voltage, which is 0.6 to 0.7 volts. The current starts increasing. And I'm going to draw this out like this, exaggerate the slope, and it looks like this. So this is forward bias, forward characteristics, right? And this increase in voltage is in millivolts or less. Okay, very, very small for most diodes. Whereas in the reverse operation, once the junction breaks down, it is a far steeper slope. So this is reverse characteristics. And in reverse, it's not true representation. Let's try it like this with a slight angle. It looks almost like this. Okay, and that's reverse. And the slope is far steeper. It's almost constant. So the voltage remains near constant. Okay, once the junction breaks down in reverse bias. This is true of any diode. Okay. So again, we have a normal silicon diode, two terminals, anode and cathode, and there's a junction between them. When you bias them in the forward direction, current starts flowing. It requires a certain amount of voltage to turn on, after which the current starts flowing. The increase in current and the increase in voltage is not linear. So a large amount of current starts flowing for a very small increase in voltage. When you reverse the terminals, meaning you are operating the diode in reverse breakdown mode, there is no current flowing from the anode to the cathode or the cathode to the anode. Okay, until we reach a point where the junction between the two terminals completely breaks down. And when the junction breaks down, that's when a large amount of carriers flow through, meaning a large amount of current is now flowing through the diode, but it's in the opposite direction. We are applying the opposite or the reverse voltage, and so current flows similar to that reverse direction. And that point is known as the reverse breakdown voltage. For typical diodes, that reverse breakdown voltage is tens of volts. A regular silicon diode that we use, it's up to 50 volts. So there is a series of diodes starting with the number 1N4001, which has a reverse breakdown voltage of 50 volts. So you could safely apply up to 50 volts in reverse to the diode and nothing will happen. Okay, junction will not break down. You will not see any current flowing through it. There's another diode after that, which is the 1N4002. So again, 1N4001 has a peak inverse rating, peak inverse voltage, or peak reverse voltage. PIV or PRV are both used interchangeably. Is up to 50 volts. The series goes up to 1N4007. The PIV rating for this 4007 is 400 volts. You could safely stick it into a wall outlet and nothing would happen to it. Okay. But regardless of what the diode is, once it breaks down, a large amount of current is flowing through it while the voltage remains near constant. Okay. The slope is far steeper than the slope that you obtain in forward bias. Okay. So now there are some diodes that are specifically formulated to operate only in reverse bias, where the junction breaks down at far lower voltages. So they are created specifically to operate in reverse mode. Okay. And the reason we do this is because the voltage is held at a near constant level. Okay. It can withstand large amount of current flowing through itself, but it'll keep the current, it'll keep the voltage across its terminals constant. And those diodes are known as Zener diodes. Zener diodes have a very similar symbol. You have the arrowhead and the cathode, but the cathode symbol has whiskers on it. Okay, this cathode symbol has whiskers on it. Typically, those whiskers are not straight. They have an angle, so something like this. Okay, so the cathode has whiskers on it. That's the symbol for a Zener diode. So 1N4001 and 4007 are regular diodes. They are not Zeners. Okay. And so there are many applications for Zener diodes, primarily in power supplies, where we want a constant voltage to come at the output. And so we use Zener diodes in power supplies, voltage regulation, clipping circuits. Okay. So here's a Zener diode. Zener diode is connected to a resistor and a voltage source. So it's a standard VRD circuit that we have seen before. As shown in the power supply, is the Zener diode forward bias or reverse? As shown in the circuit. It's forward, right? It's a standard diode. It's connected in forward bias. And so we can apply circuit analysis techniques. And we can calculate what the current or the voltage across the resistor would be. 1N750, typical silicon diode, we can say forward bias is around 0.6 to 0.7 volts. So diode voltage VD, let's just use 0.7 volts. So then what is the voltage across the 620 ohms? Across the resistor. You apply KVL, 10 minus 0.7, so 9.3. And then of course you can find, so we found the output voltage, you can find the current by applying Ohm's law to that resistor. And for power, P equals VI. Once you have I, multiply it with 0.7, multiply it with 9.3, and you have the power dissipation rating for that diode. Anyway, this is not important right now. It's a VRD circuit that we have seen before. The important point here is to show that Zener diodes are just like regular silicon diodes. Okay, when operated in forward bias, they behave the exact same way that we have learned so far. Right, so no difference, exactly the same. But what happens if we reverse the polarity? Now we are connecting the we are connecting the Zener diode in reverse bias or reverse mode of operation. What should change with regards to the operation? Let's take a pause while you think about it. And then let me know if you have any questions. Any guesses? Any questions? Same point. Yeah, both of you are correct. So in terms of operation, if you want to just look at it as an off-the-shelf component, there is no difference. Forward bias diode requires 0.7 volts to turn on. Reverse bias Zener diode requires a certain amount of voltage to turn on. That's the way we should look at the circuit. Okay, that is the way we should look at the circuit. So the Zener diode 1N750 has a voltage rating of 4.7 volts. Why? Right here. Okay, that means that the junction of this diode will break down at 4.7 volts. Again, regular silicon diode, the lowest one, breaks down at 50 volts. Zener diodes are specifically formulated and manufactured to break down at specific voltages. Okay, and that is something we look at in 315, just a little bit of that process. But for now, suffice it to know that if you're looking at a Zener diode, forward operation is exactly the same as a regular diode. Reverse operation also, we can look at it in pretty much the same way as forward bias, except now the voltage will be specified as a Zener voltage rating. So if you buy a Zener diode off the shelf, you can go to any website, go to any manufacturer, and you can look up Zener diodes and they will say, oh, VZ, Zener diode voltage, VZ, with a rating of 5 volts, 6 volts, 7 volts, 8 volts, 4.7, 6.2, 8.9. Many different voltages can be found off the shelf. Okay. And we can think of them as the diode turn on voltage in reverse bias. All right, so I'm going to take a pause. I'll write down a few things. What do you think over that? Let me know if you have any questions. Okay. Good point. That's going to be the next step. Yeah. And then current I is flowing in the same direction. So as far as analysis goes, Zener diode analysis in a VRD circuit follows pretty much the same path that we use for regular diodes. The only thing is the diode is flipped. But as far as calculations go and as far as understanding goes, there is absolutely no difference. Okay, there's absolutely no difference. You're applying a 10 volt supply to the Zener diode via the resistor. Once the voltage crosses the turn on voltage, which is 4.7 volts, the Zener diode will start conducting, current will start to flow. If it's below 4.7, the diode will not turn on. That's all it means. So once it starts conducting, VZ, in this example, VZ is 4.7 volts. So what is the voltage across the resistor? That's it, 10 minus 4.7. And then, of course, from there, we can find the current flowing through the circuit. Does that make sense to everyone? Have you all performed a lab experiment with Zener diodes? Okay. Was it a voltage regulator? What kind of experiment was it? Voltage regulator. Okay. Any questions? Oh, good. Okay. So here's a special thing though. Um, in a regular diode, let's say if we connected it in forward bias, turns on after 0.6, 0.7 volts, right? What happens if you increase the voltage? Supply voltage, I mean. If you increase the supply, let's say we are applying 10 volts, diode turns on at 0.7. What happens? Let's say we start at 0, right? 0 volt supply voltage. Diode is off, circuit's off, everything is off. We increase the supply voltage from 0 to 0.5. Diode might start conducting just a little bit. This is in forward bias. Right? Once it crosses 0.5, 0.6, 0.7, 0.8, diode turns on completely or fully turns on. Current starts flowing through the diode, through the circuit. Current increases, right? Now, if we increase the supply voltage from 1 volt, 2 volts, 3 volts, 4 volts, what happens? Power supply resistor is linear. You increase the voltage, current would increase. So current to the diode will also increase correspondingly. At the same time, the diode voltage is not going to remain near constant. It's going to increase from 0.7 to 0.71, 0.72, 0.75, 0.8, perhaps 1 even. So the higher you go in the current, the voltage is going to increase. There is a slope to the diode curve in forward bias. However, for the Zener diode, when you increase the voltage, let's say we start from 0, same thing. We start from 0, diode is off. You go to 1 volts, 2 volts, 3 volts, diode is still off. 4 volts, 4.5, 4.7. Now here, the diode does not increase slowly. When you hit 4.6, diode is still off. 4.7, it's like a switch flips, junction breaks down, and current starts flowing through it. And the current remains, sorry, not current, the voltage remains at 4.7. So now if the supply voltage increases from 4.7 to 5 volts, 5.5, 6, 7, 8, 9, 10 volts, well, the diode voltage will remain near constant at 4.7. But if you're sending more voltage to the circuit, that means more current is flowing to the circuit. So the Zener diode is going to sink more current through itself, but it'll keep the voltage across its terminals at a near constant. If you apply KVL to the circuit, where is that extra voltage going? There's only one other component, the resistor. So, and then it fits with all the known laws that we have, right? Resistor follows or obeys Ohm's law. If voltage increases, resistance remains the same, the current must increase. So the current increases through the circuit. The diode, being a nonlinear device, will accept more current flowing through it, but it'll keep the voltage constant. The rest of the voltage is dropped across that resistor. So the resistor voltage correspondingly increases and everything is balanced out. Does that make sense to everyone? And that is also what you saw in voltage regulation. Voltage regulation means, or regulating simply means, no matter what happens at the input, you're regulating that input to give a constant output. Hence the term voltage regulation. Okay, let's take a pause. What do you think over that? Let me know if you have questions. Yes. That is correct. So the question being asked is, or more of a statement or a clarification, is that the Zener diode sinks more current to itself, but it keeps the voltage constant. The rest of the voltage drops across the resistor. Right? Is that the question? Yeah, that is correct. Yeah, that's how it works. And then, of course, also as you stated, one part of the statement was until it reaches a certain limit, which is what I'm going to talk about next. If there are no other questions. Okay. All right. So as we stated, I think a couple of different students made the same point, is that what is that limit? Right? We're talking about electrical energy. As with all circuits, when electrical energy is transferred to the circuit, there's always energy dissipation taking place in the form of heat. Electrical energy is dissipated in the form of thermal energy, converted into thermal energy and dissipated as heat. So that is an unavoidable consequence of energy transfer. So all diodes, all resistors, all components come with a power rating. That power rating tells us how much voltage and how much current it can withstand. So Zener diodes, not only do they come with a voltage rating VZ, they also come with a power rating called PZ. And this PZ, of course, is VZ times IZ. Power, of course, is the product of voltage and current. So Zener diode, PZ is VZ times IZ. And that places a cap or an upper limit on how much current that Zener diode can withstand. Because VZ is going to be near constant. So if you have a 5-volt Zener diode with a 50-watt rating, we can easily calculate how much current it can withstand. And that is the upper limit of operation. And of course, that is also true of any device, not just the Zener diode. Okay, so the Zener diodes that you used in the lab kit, I'm not familiar with, I'm not sure what that voltage rating was, but it has a power rating. Okay, so when you go to buy these components, there's always a power rating associated with it. Okay, let's take a look at a circuit where we have two Zener diodes connected back to back, and we apply a AC waveform to it. Okay, we apply an AC waveform to it. So let's say we have the circuit, right? Resistor. And you're taking the output across here. And they're both the 1N750. Okay, so this is V in, this is V out, plus minus at the right. And V in of T is a sinusoidal signal, AC signal. 10 volts peak or 10 VP, that means the negative also is this will be minus 10 VP. The actual value doesn't matter. Okay, let's just call it plus and minus 10. Makes things simple. So So how does this circuit work? Well, we analyze using the same techniques we used previously. We see whether for each half cycle, which diodes is forward bias and which is reverse bias. Okay. If we isolate this branch, what do we see? You have one diode going this way, the other diode going this way, right? That means to have a clear pathway through both the diodes, one diode is forward bias, the other diode is reverse bias, right? One diode is forward bias, the other diode is reverse bias. So in forward bias, the diode voltage drop is 0.7. In reverse bias, that same diode will require 4.7 volts. And they are connected back to back. Actually, it's not back to back, it's like front to front in that sense, cathode to cathode. So at any given point in time in the circuit, both diodes will never be forward bias or both will never be reverse bias. One or the other must be forward and reverse, right? So the total voltage drop across that branch is 0.7 plus 4.7. That's 5.4 volts. You need a minimum of 5.4 volts to turn on both diodes. And because they are connected in the same series branch, it's an all or nothing proposition, meaning both the diodes will be on at the same time and both will be off at the same time, right? So the voltage must go above 5.4. Below 5.4, the diodes are off. And then V out is exactly the same as V in. So if I was to draw out the output waveform on here, let's say this is 10, half here is 5, and I'm just going to say this is 5.4. My output will look something like this. And let's say this is minus 10, and this is minus 5.4. Did you all do this something like this in the lab? You did? With two Zener diodes? Yeah, it would be something else, I would guess. Not this kind of circuit. Okay. So sine wave input comes in, let's say positive peak plus 10, negative peak is minus 10. As long as the value of the input is below 5.4, diodes are off. So V out is equal to V in, right? So if V in is 1 volt, V out is also 1 volt. V in is 2 volts, output is 2 volts. If it's 1.113 volts, output is 1.113 volts until it crosses 5.4. Once it crosses 5.4, diodes turn on, becomes a short. Everything goes through, all the current flows through the diode, nothing goes to the output. The only thing at the output is a constant level of 5.4 volts. So see 5.4 volts, and then same thing happens in the negative cycle. So you have a clipped waveform. So remember, we talked about diode clipping circuits. This is another kind of clipping circuit. It's clipped. Let's take a pause while you think over this, and I'll also pose a question to you. We have seen a clipping circuit previously at a certain voltage level. What is the advantage of this circuit over the previous one? Excuse me.
I have a question.
Yes, go ahead.
Can you explain why they both have to turn on or off at the same time?
Sure. So one diode is forward bias, the other one is reverse. And because they are facing not in the same direction, they're facing in the opposite direction. So they both can never be forward at the same time, and they both cannot be reversed at the same time. It's just physically impossible with this circuit, right? And so with the way the circuit, with the way the two diodes are configured, one will be forward bias, the other one will be reverse bias. So let's say we apply positive 10 volts to the circuit. If V in is plus 10 volts, or let's say not plus 10 volts, let's say it's 0.7 volts. Well, if you apply 0.7 volts, you have 0.7 volts here, it's not enough to turn on both diodes because the diode at the top, this will be forward bias. It requires 0.7 volts. This one would be reverse bias. That requires 4.7 volts. So V in must be greater than 5.4 to satisfy both this diode and this one. Does that make sense to everyone? If it's not above 5.4, let's say if it's 5.3, well, both diodes will be off because it's just not enough to turn on the diodes. Does that answer your question?
Yeah, thank you. So they're kind of just combined.
Yes, combined.
Thank you.
Yes. Sure. So why is it a limitation or why is it clipping? So the clipping portion comes from so V out, this is the only thing we're going to see, V out. So the question being asked is about why does clipping occur? So what I want to say is that below 5.4, V out, the waveform in red, has the exact same value as V in. So V in is 1 volt, output is 1 volt. If it's 2 volts, it's going to be 2 volts. 3 volts will be 3. If it's 4, it's 4. Right? And so V out follows the same pattern as V in. But once it reaches 5.4, the diodes turn on. And when the diodes turn on, if this was ideal diode, it would behave like a short circuit. So our V out would be 0. But these are Zener diodes connected. Well, one is forward bias 0.7, the other one is 4.7. So the voltage is going to remain near constant. So it will remain at 5.4. Okay, so V in could increase. V in could increase from 5.4 to 6 volts. Diodes are still on and maintain 5.4 across its terminals. And so no matter what happens, we still, V in could go up like this. It's all above 5.4, but the diode voltages remain at 5.4. And that's why we only receive 5.4 at the output. And the increased voltage will go through the resistor. So at the time when V in goes above 5.4, let's say 6.4, 7, 8, 9, 10 volts, all of that extra voltage is dropping across the resistor. So sinusoidal waveform reverses and it goes minus 5.4. And so in the negative half cycle, the bottom diode will be forward bias and the top diode would be reverse bias. Okay. So positive half cycle, I'm going to write it. Let's see. Let's write it here. Let's call this D1, D2. In positive half cycle, D1 is forward bias, D2 is reverse bias, and in the negative half cycle, D1 is reverse bias and D2 is forward bias. And that gives us 5.4 in both directions. Okay. All right. Okay, moving on to op amps. I'm going to talk about op amps. Op amps, similar to comparators, have a large triangular symbol, but there is no transition symbol inside the op amp. Typically, we have what is known as the inverting input and the non-inverting input. So minus, plus, actually, you know what? Let me follow the symbol that's on there. So V in plus, V in minus. The plus is known as the non-inverting input terminal, and the minus is labeled as the inverting input. Okay. V out is taken on the right, and then you have the power supply rails. The power supply rails are more often than not never shown in an op amp or comparator circuit. Not unless we are trying to show something specific. Plus VCC minus, well, using VDD. So let's use VDD minus VSS. Okay. So there are some characteristics of an op amp. Here are some of them. The first is that it has very high input resistance. So at the input terminals, which is V in plus and V in minus, it has very high resistance. So the input currents going into the op amps are typically negligible or almost equal to zero. Okay. And in many theoretical analyses, we assume that the input current is going to be zero. Right? Input current means the signal that we are applying at the input. That signal could be DC, could be AC. So where is it getting the rest of its energy from? It's coming from the power supply rails. So the internal currents that flow through the op amp, they're coming from the power supply rails, VDD and VSS. Okay. But as far as input goes, if it's AC or DC input at the V in plus and V in minus terminals, those currents are very small. So two characteristics: very high input resistance and very low current at the input terminals going in. Okay. In a comparator, let's see. Not here yet. Come on. No. Oh, there you go. Jumped one slide ahead. So in a comparator, the output goes either to the positive supply rail or the negative supply, right? If you apply plus minus 5 volts, the output is either plus 5 volts or minus 5 volts, depending on which V in terminal is higher or lower, right? The op amp can be used as a comparator, but it is far more than a comparator. This illustrates a little bit of the internal construction of a comparator on the left and an op-amp on the right. Op-amp, by the way, anyone know the full form of op-amp? Might have mentioned this before, you might have learned it in the lab perhaps. Amp is amplifier, operational. Yep, there you go. Put it together. It's operational amplifier. It can perform a variety of mathematical operations like addition, summation, subtraction, difference, differentiation, integration, and then of course amplification. It's a very critical or very important component in electronic circuits. Okay. So again, for a comparator, the output goes either plus VCC or minus VSS or minus VE. So positive supply or the negative supply. So its output's kind of like a rectangular waveform. Op amps, however, far more than comparators, they are designed to actually have outputs in the middle of the supply range. Meaning if you apply a small AC input to it and we wish to amplify it, then you have a larger AC output, similar to the input terminals. And so comparators operate at only 2 levels, whereas op amps work between the 2 power supply rails. If an op amp output touches the power supply rails, either positive or negative, we say that it is saturated, which is actually not desirable. Right? It's not actually desirable. The op amps, similar to comparators, have positive as well as negative input terminals. In an op amp, the typical configuration takes the output and feeds it back into the input, one of the input terminals. Okay, so in an op amp, the output is fed back into the input. So that is known as feedback. If the feedback is connected to the positive terminal, Vin plus, it is known as positive feedback loop. If it connected to the negative terminal, then it's known as a negative feedback loop. Most op amp circuits use negative feedback. Positive feedback reinforces, whereas negative feedback reduces. Okay, so for amplification, we use negative feedback. Positive feedback is used when we want to design oscillators. Oscillator circuits use positive feedback. Okay. So again, here, op amps use negative feedback. We want to intentionally reduce the input. Okay. The output source and sink capability of any or most op amps. Sourcing means providing the current. Sinking means, well, as the name suggests, you're receiving the current. Okay. The Zener diodes that we just talked about and the ones that we use for voltage regulation, they're acting as current sinks because they're permitting the current to flow through themselves so that the other components are protected. Right? So it's acting as a current sink. Similarly, op amps can have sourcing and sink capability. Okay. Does not have to be identical numbers. It could perhaps source more than it sinks, or it could perhaps sink more than it sources. So it just depends on the application. VDD goes in, so it sources out of the op amp. VSS, negative supply rails, goes out, and so it pulls or sinks current from the output. Okay. Typical current capability is 10 to 20 milliamps. There are higher powered devices too, but depends on the application. Typical ones that we use in the labs and for circuits, they are 25 milliamps or less. Okay. And let's see. We are out of time, so we'll end here today. We'll pick up here on Monday. There's some material that needs to be covered, and so I am leaning towards not having a quiz on Monday, but it'll be a full class as in like full 50-minute class. Okay. If I do decide to have a quiz, I will let you know by tonight, but more like Most likely I'm not to have a quiz. Okay. My target goal for every quarter is usually 8 to 9 quizzes or 7 to 9 quizzes. So we are right around 8, which is like the perfect number. So it works just fine. All right. Have a good weekend, and I will see you all on Monday.